we present tomatoes, a framework for topology and material optimization of latent heat thermal energy storage devices. The motivation for this work stems from a critical global challenge in energy storage. To ensure power grid stability, especially with the rise of intermittent renewable sources like solar and wind, and to effectively capture waste heat from industrial processes, we require efficient thermal energy storage solutions. Latent heat thermal energy storage or LHTS provides a promising pathway. These systems are highly appealing because they are cost effective, contribute to improved sustainability, and offer high energy density. Let's examine the design of a typical LHTS device. It consists of three primary components: a phase change material, that is PCM, that stores and releases this energy by melting and solidifying, and a heat conducting material, HCM, which forms a structural matrix to enhance heat transfer, and a heat transfer fluid, HTF, that transports thermal energy. The choice of PCM is critical. Commonly used materials include paraffins such as alkanes, eutectics such as a mixture of lauric and myristic acid, and inorganics such as salt hydrates. Relevant materials are chosen based on their thermal energy storage capacity, melting temperature, and other thermal characteristics. Similarly, the HCM, often metals, are chosen for its high thermal conductivity. The optimal design involves the geometric configuration and the choice of material. The core design problem is a fundamental trade-off. The HCM possesses high conductivity but offers low energy storage capacity. Conversely, the PCM has high energy storage but suffers from low thermal conductivity. Therefore, an optimal design consists of both the HCMs and PCMs. Furthermore, the system performance depends not only on which materials are chosen but on how they are spatially distributed. This co-design of material and geometry is now becoming feasible due to significant advances in manufacturing. Additive manufacturing allows for the fabrication of highly complex multi-material structures as seen in these examples. This capability contrasts with conventional manufacturing methods, which are typically limited to simpler extruded or fin geometries. This new manufacturing freedom unlocks the potential for optimal designs. In parallel with manufacturing, we are witnessing advances in materials science. There is a vast and growing database of phase change materials, each with unique properties. Likewise, there is a massive availability of potential heat conducting materials offering a large range of thermal characteristics. This vast selection presents our central computational challenge. We have discrete material datasets. However, gradient based optimization, the engine driving modern topology optimization, requires continuous and differentiable parameters. This paper addresses the central challenge of optimizing from a choice of discrete material list in addition to conventional geometry layout tackled in topology optimization. Our solution is to create a differentiable material database representation. We take the discrete material database and map it to a continuous representation using a variational autoencoder. This model learns to compress all the complex properties of a PCM, such as the conductivity, latent heat, and melting temperature, into a compact continuous latent vector. The decoder network can then reconstruct the full material properties from this compact vector. Critically, we observe that the decoder is a differentiable mapping between the latent space and the material properties, thus enabling us to use them in a gradient based optimizer. We repeat this exact process for the heat conducting materials. A second VA is trained on the HCM database, learning to map its relevant properties into a separate continuous latent space. Now, instead of choosing from discrete lists, our optimizer can search two continuous latent spaces to find the optimal materials for our design. For the geometric design, we use a pseudo-density representation. The design domain is discretized into a grid of elements. Each element is assigned a design variable gamma, ranging from 0 to 1. A value of 0 represents pure HCM, while a value of 1 represents pure PCM. Intermediate values represent a smooth mixture of the two, which is essential for gradient based optimization. We now illustrate the entire co-design optimization loop. We begin with our design variables, the pseudo-density field for the geometry, a latent vector for the PCM, and a latent vector for the HCM. The latent vectors are passed through their respective trained VA decoders. This reconstructs the full list of physical material properties such as thermal conductivity, latent heat, density, material cost, and melting temperature. These properties, along with the density field, are fed into a transient nonlinear finite element analysis solver. This simulation yields the temperature history and the stored energy profile over the discharge time. From this simulation, we compute a loss function. This objective measures the thermal performance, for example, maximizing the energy discharge subject to a constraint on the total material cost. Crucially, we use automatic differentiation to compute the gradients of this loss with respect to all the design variables, the geometry field, and both material latent vectors. These gradients are used by an optimizer such as Adam to update the design for the next iteration. This loop repeats until the design converges, yielding an optimized material distribution and the corresponding optimal materials from the database. We now demonstrate the co-design approach by comparing it to a conventional sequential design process. A sequential process might start with a base design. A designer might first optimize the geometry, then sequentially select a new HCM and then a new PCM, ultimately reaching a design. In our example, we see a design as illustrated in panel C with boron nitride as our HCM and X90 plus ICE as our PCM. Critically, we observe a net energy discharge of 268.5 megajoules. However, our co-design framework optimizes the geometry and material simultaneously. This concurrent approach finds a coupled solution that is superior, discharging 298 megajoules. We illustrate the discharge curves for the different design processes. The blue dashed line A represents optimizing only the geometry. The red B and purple C lines show the sequential material selections. The green dashed line D representing our code design clearly shows a much larger energy discharge. We observe an improvement of 11% in the final performance comparing the sequential and concurrent design paradigms. We now explore the Pareto trade-off between competing objectives and cost. By running the optimization with different maximum cost constraints, we can generate a Pareto front. This curve reveals the maximum energy discharge achievable for a given budget. As the cost constraint is relaxed, moving from left to right, the optimizer not only optimizes the geometry but it selects different materials. This provides designers with a full suite of optimal choices, not just a single point solution. In conclusion, we introduce a framework for the co-optimization of material selection and topology for latent heat thermal energy storage devices. A key contribution is the use of variational autoencoders to map discrete material databases for both PCMs and HCMs into continuous and differentiable latent spaces. And third, the results demonstrate that this co-design framework yields LHTS designs with superior thermal performance compared to conventional sequential design workflows. We are actively extending this work in several key directions. We plan to expand the framework to a geometry material process co-design by integrating manufacturing constraints and process parameters. We are also extending the framework to 3D, then adding the co-selection of the heat transfer fluid and moving towards experimental validation of the optimized designs. We also acknowledge the current limitations. The material databases used were illustrative and the thermal model was limited to conduction, neglecting the effects of convection, which will be an important focus of future research. For more information on the work and the source code, see the GitHub repository at the link shown.